Here we are going to apply the Hartree-Fock approximation for the uniform electron gas. So first, let's remember which are the Hartree-Fock equations that we already got. These are these equations that we need to solve in order to get an expression for the electronic wave functions. So again, let's remember which are different terms arising here. This is like a kinetic energy term. This is the term coming from the interaction between the electrons and the ions. Then we have the Hartree or direct term, which will be called UH. Then we have the exchange term, which is called UX. So if we consider the uniform electron gas, where the ions are substituted with this uniform positive background, the interaction between the electrons and the ion is given by that expression, where the charge density of the ion is, or the ions or the nuclei, is N over V. So we have to solve that equation. That, as it happened in the Hartree approximation, the Hartree-Fock approximation, actually, these solutions can be proved that they are also plane waves, and they are degenerating the spin, so the spin state can be anyone. I consider spin up and down. And we are going to prove actually that these plane waves are actually solutions of the Hartree-Fock equations. So for that, basically what we have to do is we have to plug these plane waves in the Hartree-Fock equations that we have seen before. So first of all, as we already saw in the case of the Hartree approximation, the ionic contribution, the ion electron contribution and the Hartree contribution, they cancel each other. So basically, as the kinetic energy term is just proportional to the, as you can see, it's proportional to plane waves. In order to prove that the plane waves are the solution of the Hartree-Fock equations, we have to see that the exchange term, this UX, is actually going to be proportional to Psi, so the plane wave associated to the I state. So basically, we're going to do so. That's the exchange term here. We're going to plug here in these wave functions. We are going to substitute them with plane waves, and the J state, or the J or I state, is going to be labeled by the K wave vector. So J is going to be Kj, and I is going to be Ki. So just substituting that's the expression that we have. We're going to rearrange that, and for that we are going to make a variable substitution. So we rename the variable. This r minus r prime we are going to call u, and we make that change. You will see that doing that variable change, you can see that this term here, this is proportional to the Psi state. That's the Psi state, and this is the prefactor multiplying the Psi state. So as you can see here, so we're proving in this way. Actually, it's very interesting to show that how you're manipulating these equations here in order to get so. So we are proving this way that the exchange term is proportional to Psi, and therefore these plane waves are actually solutions of these Hartree-Fock equations. And now we're going to analyze which are the eigenvalues associated to these Hartree-Fock equations. So again, in order to get so, what we are going to do is we are going to plug in these Hartree-Fock equations for the uniform electron gas, where to basically have the kinetic energy and the exchange term. We are going to substitute them with the plane waves. We do that, and that's the expression that we have. Where this expression here is the one we had before as a prefactor. Sorry, this one is included here as a prefactor multiplying the plane wave associated to the Ki state. Okay. So we have to rearrange that. We have to do these integrations here, and we have to do these summations here. So first we'll do the integration over u, and doing the integration over u, we have that expression here. So basically what we have here is the Fourier transform of the Coulomb potential, 1 over u, or 1 over r in this case, and the Fourier transform of the Coulomb potential is 4 pi over the transfer moment over q squared, where q in this case is the momentum difference. And we have to do the summation over all occupied state, this occupied, occupied by the electron, this kj, the occupied kj states. And the occupied kj states are going to be all, we are naming here, instead of calling it kj, we're calling k prime here. And the occupied k states are going to be those states lower than the Fermi wave vector. So we have to do that summation over k prime states lower than kf. Doing the summation, we know already it's a tough thing. What we have to do is you have to substitute that with an integral, and we know how to substitute that with an integral. After doing that, considering the number of states per unit volume in the k space, that's what we have. This is the term that we have, which is equivalent to this term above. And doing that integration, we can see also it's quite thick integration here. You can see that this term, after doing the integration, we are getting this contribution here, where this f vector or f function is this function here. So this way we are getting an expression for the eigenvalues in this Hartree-Fock equation. The first term is coming from the kinetic energy, we know that, and there is an extra term which is also negative here. Remember that exchange contribution is usually negative, and you have an extra contribution coming from the exchange. So we have an additional term here, which is going to be interesting, just coming. Remember that the exchange term is just coming from the antisymmetry of the wave function and is associated to the exchange. Now this is the first step. So the second step here, which we'll be analyzing the following, is going to analyze, which is the ground state energy within the Hartree-Fock approximation, which actually is going to be, because of this extra term, is going to be a bit different as the one in the uniform electron or the free electron gas approximation.